All right, we're gonna start recording. It's officially 9 o'clock. So, so today we are going to take a look at chapter 21. Let's pull this up here, and we're only going to go about halfway through it. There's a lot of, I know you guys will be excited. There's a lot of new concepts coming in store for you here. Uh, but we'll take our time with this one. Actually, this one, from my perspective, this chapter kind of brings everything together. It's the start of bringing it all together. The next couple of chapters, we're going to actually examine the components we've been looking at. Now, I mean, up to now, we've been studying like the properties of, of the components, and getting used to working with the formulas, what we expect to see with these things and stuff. And so the next three labs, we're going to basically, it's going to be RLC circuits where we're going to do all three together. I'm essentially I want to hand out three labs to you guys tomorrow, which will be like our next week and a half's worth of labs. But but we'll take our time. I mean, we have time. So, let's dig into it and take our time and really, get our learning out of all this and everything. But we'll be doing a series, a parallel, and like a series parallel configuration for all three. And so it's a little ties in with this chapter, and it's a little bit before it in certain respects. And if you notice, he didn't spend like we only did two chapters really with inductors, if you think about it, and then three chapters were capacitors. But um, yeah, I get it. The inductors, you're kind of rehashing and stuff like that. But so at this point, now we're going to start looking into some of the nitty gritty of as you can see by the title here, RC and LR time constants. I know, I'm so excited. I know you are too. Woo. But now we'll go. Yeah, I know. So now we'll go up to right about here with the RT time constant and the charge discharge curves, and then we'll continue the rest of it on next week. So we'll just take our time with this, like I say, because this is a lot of new stuff, if you will. Because now we're going to be looking at overall responses and coming up. Yeah, we go. So essentially, something that I sort of harp on is about like resistance alone. Okay, so we're going to take a look at that, and then we're going to introduce the LR time constant, take a look at it, see what kind of cause and effect, if you will, and then we'll look at the RC time constant. So there's quite a bit here, and then like I say, we'll leave the rest of this for next week to discuss, and then of course we'll be following this up with labs and looking at wave shaping, how we can control wave shaping. It's an interesting phenomenon, and it's one of the primary uses that you would do with these type of circuits, um, controlling the wave shapes and the time involved and the discharge. But we'll get into that. But so we take a look at it, right? The neatest thing about resistance, he's like old reliable. Okay, resistance only has opposition to current. Okay, and as you see, there is no reaction, right? The inductor and the capacitors, now they react, they respond to stimulus in different ways and whatnot. But a resistor, he's like the old reliable. He's just tried and true and does his thing. But there's nothing really special. It doesn't change our wave shapes, if you will. I mean, just like in DC, essentially we pass a current through it, it develops a voltage, whether it's DC or AC. So we don't get, like I said, a very bottom point here, we don't get a magnetic field going on, like in the case of an inductor. We don't get a charge buildup or anything like that in the case of a capacitor. So he he does not oppose either voltage or current. Um, Basically, we pass the current through, we develop a voltage across it, get our work done across the resistor, and on we go. So, I mean, really, the biggest thing we're going to get here is, depending on our charge, right, is how much heat we'll get coming off of the resistor, and that's about the most exciting thing we're going to have happen here. So that is the neat thing about the resistor. There's no phase change, magnitude changes, right? Because we are developing across it. But outside of that, as far as time response and whatnot, he has no effect. So he's like our stable point, if you will. So now we kind of go back to basics here. See, this is such an odd chapter, but it had to go somewhere, I suppose. So if we look at the first circuit here, all right, that one we should know pretty well. We got us a nice DC energy source of 10 volts, a little manual switch right there, and a resistor of 10 whole ohms. And then what we're going to do is we're going to basically, like he has here, we're going to examine the response. So when we close the switch, what is going to happen? Well, not much, but no, what we'll do is when we close the switch, we allow current to flow through, and we can see it's a steady state, okay? There are no changes. If we go and look at the response over time, if we look at 0.1 seconds, it's going to have one response. We look 1 minute out, it's going to have the same response. So as far as time concerns, it's the same. We can come up with one equation for this bad boy, and we're pretty much done. So once we close the switch, you can see it goes from 0 to 1 amps instantly, or practically instantly, right? As current flows through, we get the electrons flowing in there, and away we go. So and that's why we don't really examine the resistor alone. I mean, we did in the very, very first lab when we were looking at characteristic waveforms, but that was just to set us up with something steady while we analyze the properties of waveforms. But yeah, these guys are overall pretty boring. I mean, we can rely on them. They don't do much. So now the exciting part happens is when we introduce our other components. In this case, we're going to take a look at what the inductor's doing overall. So, I mean, the key point here is time constant. So how are we going to examine that? So let's take a look. So if we have an RL circuit, so we have a resistor and inductor in a circuit. Basically, we know the inductor is going to have a certain opposition, a certain reaction, if you will, to current. So we get a build up, and we actually get a response over time. And again, that's something that can be measured as well, and it is something that we can rely on. But a new term for us here is going to be the transient response, okay? So what the heck does that mean? So as he states here, it's a temporary condition that exists only until the steady state current is reached. Steady state, right? Which was this. That's a steady state. All right. So as I say, it is only a temporary condition. So it is going to be subject to change, and it will change. Basically because we have an AC signal going through, and it will cause things to happen, if you will. So when we look at the transient response, measure it in terms of the ratio of L over R, okay? So what this is basically is trying to figure out what the particular time constant is of the circuit that you're involved with. So we see a new formula here, see, where we got T is equal to L over R. That is our ratio. So it's a time constant, measure how long it takes the current to change by this much. So it has to go through a fairly drastic change before we consider an effective change. But so remember this part, that it's to do with our time constant, okay? And then we're going to get into what the heck does that actually mean. So here we see the same circuit as we had before, but now we throw the inductor in here. Okay. So now remember, this is a DC charge. We're not going to get much in the way of change. It's going to take it time to build up. Okay. See how it does here? So like with the resistor, we seen virtually instantaneous and it reached steady state instantly. Okay. But by the graph here, we can see that the inductor doesn't quite go along with that. So the time it takes before he gets to his steady state, if you will, see, look at that, half a second. Whereas we go back and look at this guy, see the graph on that current, he was ready to go right from the get-go. But excuse me, comparing those two graphs, we could see, oh, look at that. And so like he said, it's how long does it take before we get to 0.63 of that charge? And we look at it this way, well, it's 0.1 second. And before we get to what they call like a settled state, when it reaches full maximum would be the half a second. But the time constant factor that we are going for would be like right here. So how does he state this? When the switch is closed, the current changes as I increases from 0 to what would be called the steady state. So eventually it'll reach the steady state value of 1 amp, so equal, to our energy source here because of the 10 ohms of resistance we have developed. So the inductor has no choice but to follow along because we're in a series configuration. So he has to rise up to 1 amp. But you can see he doesn't do it willingly right off the bat, if you will. He takes his time a little bit here. So that's just examining, the overall function of, or how the response time of this particular component is. And this is like one of the change ups that we see, okay? So when the inductive circuit's opened, okay, basically we're gonna throw that switch open, the time constant for what they call the current decay becomes very short because that ratio becomes smaller with the high resistance of the open. What does he mean by high resistance of the open? Basically, it approaches infinite resistance, if you will. Now we have an open circuit, so current flow is no longer occurring, right? Close the switch, we get current flow. If we wait half a second, we'll reach full steady state where it comes up to the full 1 amp of the circuit, right? And then if we were to open the switch, what would happen? Oh, that's basically what we're examining here. So what he means by the current decay. So how long does it take before this current? So if we did this with just a resistive element, if we just had the circuit with a resistor in there and just the energy source, and we open the switch up, for it to reach like the 0 state is virtually instantaneous. But if we're having the inductor in there, it doesn't do it that way. So that's what he means by the current decay. So this thing, even though we have the switch open, is still an active circuit, if you will, because now the inductor is charged. So when we look at that, that's what they mean by the current decaying. But it becomes very short because the LR ratio becomes smaller with the high resistance of the open. Because if we consider that high resistance as being a real component in this little ratio here, then we would literally be dividing that inductive value by infinity, okay, which, yeah. So, and what that division by infinity always yields a 0. So when he says it becomes smaller with the high resistance of the open, he's not kidding. It does become very, very much smaller. So what happens there, right? Then the current drops towards 0 much faster than the rise of current. So if we were to examine, so like if we were looking at this waveform, we'll see it's like a slow slope, a nice curve like that. But on the discharge arm, oh, he does not show that graph. On the discharge on, if we were to be examining it, you would see an extreme rapid fall, and it would drop back down to 0 here. And amount of time it would take would be very, very short. And again, based on this ratio, because that was our time constant. So we looked at it, how long does it take? Well, if it's almost zero, then it's going to fall fast, and we would see a very sharp decline here if we were like examining a waveform, if you will, if we could reproduce it properly, which is very difficult to do, like on an O-scope. You know, you're going to see, basically, you're going to see it fall up and you're going to see it fall down. But as far as what occurs, that's what we're more interested. So the current drops towards zero much, much faster than the rise, and that's what's going on here. So what is the result of that? So we get basically a high value and of something they call self-induced voltage across a coil whenever you have that circuit open like that. And what do they mean by self-induced voltage? Well, now we've cut off, if we open that switch, we've essentially cut the component off from a current source. So there is no energy flowing to it, but there's still energy in the circuit, because the inductor, until the time that it falls to zero, is still considered an active component because it's still charged and it's still allowing a certain amount of electron flow. And granted, it's going to fall very, very sharply, but it's not going to be instantaneous. Excuse me. So what we would have is a self-induced voltage across that coil whenever we open that like that. So what can happen is, the cause and effect here is that the voltage that we produce by doing this can end up actually being much larger than the applied voltage. And that's because of the resistivity of the components involved, and basically what we have, you know, as far as electron flow, where are the electrons going at this point? It's an interesting little thing. And that's one thing that we examine. I mean, even though these are considered passive components, they still have a certain amount of cause and effect going on here like this. And I don't know, I'm a nerd, I know. I find this exciting, but anyway. So if we take a look, now we get a little more, we're going to get a little more complicated here, right? So let's take a look at figure A here, figure 21.3. We're going to throw in a neon bulb, okay? And he states that the neon bulb needs 90 volts for ionization. You know what a neon bulb is, you know, like the, like store signs and stuff, you know, the glowy ones. Well, they don't have like an active filament. They're like fluorescent lights where they're gas filled. So when you do ionization, basically you're making the thing glow, but there's no active componentry inside of it, if you will. Basically, you're making plasma. So we would need 90 volts to have this phenomenon occurs, at which time it's going to glow. But unfortunately, yeah, look at this. We only have an 8-volt battery source, but we need 90 volts to make this neon sign glow. How do it happen? So let's take a look, see what he's got, right? So when the switch is open, the self-induced voltage, look at that. So now, you remember now, we've literally cut this thing off from the energy source, if you will, okay? So we throw the switch open, and now we're relying on basically the feedback of the inductor. And so it's charged up, and now it's gonna discharge. And so as you can see, it's going to discharge high enough that we're actually going to make this bulb, you know, it would be a very short amount of time, okay? You'll probably just see it like blink and then it's done. This would be a very interesting little lab experiment to do. I do not have any neon bulbs. They tend to be a little on the pricey side, but it is an interesting thing. And if we were able to do, you know, something like this, that is what we would have happen. And eventually, essentially, we could even play with the, you know, the value of the inductor and see if we can increase that. And you know, play with the time constant. So you'd have like a longer discharge time. And even though, you know, we're not going to be able to make it go that long, it's still, no matter what, when we open that switch, the neon bulb is going to glow. It's just going to be like bleep. But it does do it. Okay, so we have basically created a much higher energy than what we originally started with. Now, the interesting thing there is like, oh, really? So you get the voltage spike, but what about the current side of it, right? Really, there's not a whole lot. It's similar to like static electricity, where you have a lot of voltage potential, but really very small current potential. But so this is kind of the type of thing that we're going to be examining is like looking at the unique properties of these components. Because like I say, now we know like how to find, their values of their reactants, if you will, what this means for us, how they don't play nicely with others by being the phase shift. So we start going 90 degrees out of phase, it starts getting a little more complicated with these components and how they react, to our signals that we have going through them. So now look at the other side of the coin. So that's essentially what we're going to be looking at with the inductors and the resistors. And you look at that time constant factor of basically the charging and discharging. And so what happens is eventually we could essentially make a wave shape, if you will, based on the value of that. So by the time constant, what we would do is basically figure out how much of a high, basically charging up and becoming what we would call an active signal, if you will. How long that will stay like that would be based on our time constant. So we would pick our values of our components with a little care if we were targeting something like that. Okay. So now a similar phenomenon occurs with capacitor. It's different. It is different. I mean, it's capacitors. They're not inductors, if you will. And we've seen by the labs that capacitors don't act like inductors. They do have a charge and discharge time, though, if you will. So what we're going to take a look at is another thing is time constant. Now, an interesting thing here, notice that the time constant for the LR is a ratio. It's like the L over R, and the time constant for capacitors is straight. So here we have our nut and neck. So these are our two formulas of the day, if you will. So here we have time is equal to R times C. So if we wanted to basically come up with a time constant, we would have to pick our values of these two components with some care. So we see, yeah, our resistors in ohms in this particular case. The C is going to be measured in the farads, right? The capacitor's capacity to charge. And then T will be measured in seconds or whatever time base, it could be milliseconds, microseconds, whatever particular time base we're working in. And in this case, we're going to be dealing with seconds because we're going to do it like we did before, the old school way with a DC and a switch. So let's take a look at this. So here we have an RC circuit in series with a DC energy source of 100 volts and one switch. So let's say we just close the switch and we look, okay, how long, and remember the 63 ratio, how long does it take us to get to 63%? So in this case with these components, it would take us 3 seconds to hit 63%. And to get fully charged would be 15 seconds. Okay, boom, 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 boom. That would be 5 time constants. It's kind of something, well, in the future, we'll be looking at that. We oftentimes in electronics for circuits such as these filters and whatnot, we do look at 5 time constants. 1 time constant to get to the 63% or to begin the effective charge, if you will. But notice it's 5 time constants to be fully charged to the wave shape that we're going for or the charge that we're going for. So then we take a look at the other side of the coin with the switch open. How long does it take for this thing to discharge? So you can see there's actually a phenomenon going on here. And you'll notice that the capacitor does take a certain amount of time. If you look at that discharge slope there, it's not instantaneous. Like the inductor would fall off very, very rapidly. Whereas the capacitor, it takes a little time to discharge, if you will. So we build up those build up the electrons across the dielectric and the capacitor, okay? and then close the switch and allow the electrons to basically bleed off of the capacitor. So if we look, see like, oh, well, okay, so it takes us this long to charge up and this long to discharge. And that's a phenomenon for these particular components in this circuit. So, and that's what we would be looking at. And remember, if we were to do this, well, why does he throw that switch in there down there like that? If we had an energy source hooked up, the capacitor would just basically reach the full charge potential, and then it would stop, okay? And then there's no more. But if you open the switch for capacitor like that and don't give it like somewhere to bleed, it will hold that charge for an indefinite amount of time. So what we have to do is put in a secondary switch here. You'll see switch S2. We put that in there basically to allow the capacitor to discharge or give it a path for discharge, right? So give it a complete circuit to go to ground so it can discharge. Otherwise, the unique thing about a capacitor, yeah, you charge them up, you can literally disconnect them from the circuit, and they will hold the charge for a good time. I've had power supplies and whatnot when I used to work in a repair center, and you have to be careful with those because some of those have like 400-volt capacitors on them, and they will still be fully charged. They've been disconnected from the machines that they were in, packaged up, put on a truck, shipped out to us, sat somewhere and receiving, okay? And so much time before it actually gets to me, there's actually like a time frame, unless it's a rush job or something, but you're looking well over a week. And these things will be at full charge potential still. So I used to have like a really, really big ceramic resistor, when it can handle some major power. And I soldered 2 leads on it. And what I used to do is basically when I got these things in, I would bleed off all the caps. You had to be careful. You don't want to touch these. There's 400 volts. It might not kill you, but oh my God, you'll wish you were dead after you got hit by that. It's like getting kicked by a mule. that hurts. It hurts a lot. But so always be careful with these things. If you ever do work where you're working with capacitors on a fairly regular basis, yeah, get yourself a nice low resistance resistor, but really big power, kind of like those big can ones I have in the lab with the giant heat sinks on them or something like that. It would be very handy and save yourself some pain, if you will. But in any case, so if we go back and look at the RC time constant, you'll see it's a charge and discharge, and that's actually a unique thing for capacitors, and we can actually make a wave shape based on this. If we were to have like an automatic switch type function where it would bing, 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 keep switching back and forth, this thing would output where we would literally have like an AC simulated signal from a DC source. It'd be an interesting thing to do, huh? Not anyway, but yeah, we'll discuss. Basically, we'll get through the RC charge and discharge here, and that's about where I'm going to end. And then I will assign these homeworks. I did assign a quiz for you guys today as well. Like I said, I was examining it, and we're actually ahead of where I thought we would be at this point. So now we're going to take it slow and have a little more fun in the lab, if you will, and examine the properties of these things. So that way we get a really good understanding of what the heck is going on here. Because now we're getting into the actual, like, what do we do with these things? What kind of work, the stuff we've been examining in labs, it's interesting, but what do you do with it? And that's what we're going to start looking at. So continuing on with the RC charge and discharge curves here. So he refers back, I know I rambled off, I'm sorry, but so he says, if you look at the previous slide, the rise is shown in the RC charge curve because the charging is fastest, which it is. If we were to really look at it, see, getting up to that 63 point, really quick there, right? 3 seconds overall, and it's already there. Compared to the amount of time that it takes to get fully settled, if we're, So the rapid charge is right in this very first leg here. You can see that. So if we say that the rise is shown in the RC charge curve because the charging is fastest at the start and then tapers off as, you know, C starts to get to the full potential of its charge. So as C charges, its potential difference increases, which it does, you know, as it reaches that first point, that 63 volts. Now its potential difference is going to change until the next point and the next point and the next point. Okay. And so, and the difference in voltage between the VT and the VC is reduced, which affects how capable we are of charging. So the circuit is literally changing its properties as it's charging up. So each leg, let's take a look at that. So each section here, you're almost effectively dealing with a different circuit each time. So as it reaches this point, it has an effect on the capacitor, right? And then it reaches this point, another effect. And that's why each time the curve becomes a little different. So if we looked at it, you know, the first 3 seconds, we have this particular response. And the next 3 seconds, we have this, and then this, and this, and this. So what he's saying is each time that happens, it has an adverse effect on the component. And it affects its rate of charge to that point, so that we're effectively dealing with a little bit different value for each time. Overall, yes, we examine it as it is, but it is just like I say, it's a phenomenon to observe that this thing does go through. So less potential different reduces the current that puts the charge in C. The more C charges, the more slowly it takes on additional charge. And why is that? Basically, what happens is, now you got to remember, all right, so inside these capacitors, we have a dielectric of some kind, whether it's like a piece of mica, piece of mylar, or something like that. Basically, it's an insulator. It doesn't like charge. It doesn't want anything to do with charge, right? I mean, essentially, think of it. We're putting a piece of nylon in there, all right? It's like, how many times have you seen anybody charge anything up with nylon? Never, and because it's an insulator. But we can deposit stuff on the surface of the insulator and not lose it. And that's why these capacitors are like they are. So what happens is we basically are depositing all these electrons on the surface of this thing, right? And then it has to go somewhere. And so what happens is, you know, at a certain point, the insulator blocks it and blocks it and blocks it until eventually you get enough electron buildup that it goes, okay, this is all I can handle on my surface here, and I got to do something with all this stuff. And so then it goes, well, here, and then dumps it all, which is essentially what's happening. So the charge effect, and that is why instantaneously there's a lot of room. You know, the electrons have plenty of space to go to. But now after those first 3 seconds, we've got so many electrons built up, right? 63%. So now it starts to become saturated, right? Saturated. And that's what they kind of mean whenever you hear this term in the future, saturated. It's a buildup. So now we have these electrons building up on the surface of this thing. And then in the next 3, right? So now we reach a different potential. Now it becomes even more crowded or more saturated, okay? And at each section of that, until finally it reaches the full point of charge. And it's like, okay, this is all the electrons my surface can handle. And that's how they come up with the value for these capacitors. You know, you get a 2 microfarad, a 5 microfarad, and so on and so on. It's basically the physical property of the insulator inside of that component and how much capacity it has, or how much surface room there is for electrons to build up on top of it. So we had to think about that's what's occurring. And that's what he means by this. So, you know, so that phenomenon is, and, you know, it's like with anything. So as you fill it up, you know, the capacity or the room it has for that becomes less and less and less until finally there's no room at all. And it'll sit there. It'll literally sit there because it's an insulator. It's not absorbing. So the electron charge can literally sit on top of this thing until we give it somewhere to let them all go. So now again, just like with the inductor, okay, so we have this built up charge, but you look at that example, once we disconnect the energy source, we have technically an inactive circuit, right? I don't have current flowing through there. So all of that is on the capacitor. So all this discharge is occurring when there's no energy source coupled to this thing. It's basically the built up energy or electrons that it's stored up. And now that we gave it a path, it's letting them all go. And we can base that, based on the time constant with this thing, which is based on that particular component, is how long it takes before it completely empties itself. I hope that helps. So going a little bit further in here, discussing more in the discharge, right? So C loses its charge at a declining rate. At the start, at the very beginning here, let's examine this one. VC has its highest value, right? The voltage across the capacitor, and can produce the maximum discharge current, which is here, okay? Because look at that. So we're going, he's got it on a volt scale versus time, and look at from basically from 0 to 1, we're, what is that? That'd probably be about 10 volts right there. So we're going from 10 volts to practically 4 volts in 1 second. And then we go from 4 volts to a little bit over 2 in 2 seconds. So we can see our initial rapid discharge is right in that first millisecond, my bad. So in that first millisecond, we get a rapid fall, and then slowly and slowly until finally, after 5 milliseconds, this thing is bled out. And now it's fully discharged. And we can measure that. We could totally measure that. So there would be less discharge current. So as this continues to fall, our current starts to fall as well. So it would literally be on a rate of decline. But the more it discharges, the slower it does it, as we can see by the graph. And that's what he is showing us, because basically this is how long it takes for that thing to fall from like 10 volts to 0 volts is 5 milliseconds overall. But we can see, each time as we go further out, it goes a little slower. In fact, look at that. To go from literally like a little over 0 down to actual 0 takes it a full millisecond. And the capacitor hasn't changed. It's still the same component it was, but it's just part of the effect of these things. All right. And that's where I stop, because that's pretty much about halfway through this chapter. And that'll give us some things to mull over and think about and whatnot. We won't be playing with these until next week and stuff. I mean, actually, a little bit even further maybe, but that's time constants. So when we start hearing about time constants, this is what we're referring to is the charge and discharge of these components and how long it takes them to do their thing. And as you can see, it very, very much relies upon the actual value of the component. So as long as we do the ratios right, we got to remember, for inductors, it's, it's a time constant is equal to L over R. And for capacitors and resistors, it's R times C. And again, it's based on, the way these things respond and where we're putting the -90 to +90 phase angles in comparison to the resistor and a lot of other things. But that's what we're going to be examining coming up. So we go through chapter 21 and then 22 and 23. So really, we've only got these 3 chapters left. So we're going to take our time because in my eye, these will be the most important ones. This one discusses the wave shaping, charge and discharge, and the actual unique thing about these particular circuits. And then the 2 following it are actual practical applications, if you will. So we got these unique phenomenons. We understand these components now. What the heck do we do with them? And that's what we're going to start looking at is what the heck do we do with them? And in fact, I have to double check and make sure all the speakers I have in the lab are functional, but we're going to play one of our very last labs. We're going to play with like some filtering effects and use a speaker speaker with different frequencies, and we're going to build our own circuit and basically be able to control the output on the speaker, you know, or like a little police siren. We won't have a timer or anything hooked up. You'll have to do it manual with the generator, but you could play with the amount of frequency that goes with it and produce different tones. And I think it's fun. It's a very noisy day. I might bring my earplugs, but no. But no, the next 3 labs we'll be looking at, like I say, it'll be tomorrow's I'm going to hand out will be series RLC. So we're start examining all 3 together, and then following that will be a parallel RLC, and then of course everyone's favorite, the series parallel RLC, and start getting used to juggling those. And we're going to do more practice problems. So this is a little bit aside from what the book is. So we'll go slower with the book, and I will hand out practice problems for us so we can start examining these circuits. And really, I just want everybody to get used to juggling the math on them and get used to working with these circuits. So that way, when we do get into these more interesting things like the time constants and our discharge and charge capacity of these components, we'll be able to take our time and analyze these properly. And I think that'll be our best bet. But that's what I have. And then, like I say, tomorrow we'll meet and I'll pass out those 3 labs. Well, I will assign the homework today for sure. And then we'll still, you know, I'll still hand out the practice problems because we haven't done series parallel configurations and whatnot. So we'll start looking at some of that and combinational circuits and stuff. It'll still be, I mean, it's still the same stuff we're going through. And that way, you know, you can try working them out. If they get you frustrated, and we'll work them out together. And hopefully we all come together. And I'm so excited. No, I know you will be too. No. But that's it. I mean, that's what we have come, you know, looking ahead. That's what we're going to go through. So as far as homeworks, I know I've been a bear in the beginning here, just grinding us through, but I really wanted to hammer these points home so we would have enough time to actually play around and utilize this stuff. So these formulas and stuff will help, you know, make sense. But so that's what I have. And like I say, we'll meet tomorrow in lab, and I'll hand those out to you with some practice problems, because I know your weekend would not be complete without practice problems. I know, but no. But yeah, but any questions on that so far? Or let me stop sharing this so you can just stare at my ugly mug. But yeah, I'm excited. I think we'll have some good fun. I want to see some wrinkly brows in lab tomorrow, like but so. But that's where we're at, and that's where we're going. And any questions?
Yeah, where can we find the recording of yesterday's meeting?
Oh, you know, I was having a heck of a time with that for some reason. It did post for me today. I kept trying and trying yesterday, and it kept telling me the video wasn't there, even though it is on my YouTube channel. Do you have my YouTube channel by any chance?
I don't.
Oh, all right. So what I'll do is I'll post my YouTube channel as well. I'll put that on the announcement thing, and that way you could check it, you know, on your own. You don't even have to go through Blackboard. I've got other stuff on there too if you really feel like getting bored out of your skull. But but I'll put on my YouTube channel. But yeah, for some I don't know what it is. Sometimes Blackboard does this to me, and it won't recognize the YouTube link right away for some reason. And even though I'll go back on YouTube and it's there and I can even view it on YouTube, it won't pull it up. But I did post it this morning. It did come through. So it is on, if you look on the daily content, I posted a day 7.5, Eli, I don't know if you're looking at that now, but there's a day 7.5 on the daily content, and it's in there.
Okay, thank you. I'll make sure to look at that.
Yeah, look at that. And then I'll post my YouTube channel on the announcement. And then I worked it out. And so next week, when we do these practice problems, I'll be able to do this a lot better with my camera. I didn't realize the actual Zoom application has all these things on it. And I even have, that's why the stuff was backwards yesterday. It was like for some reason it had the reverse or mirror image thing. I'm getting too old school for this stuff now. but no, the next time we do this, it'll be a lot more polished. I'll have a better setup and we'll be able to go through the practice problems better. So I apologize for the video quality of this. And then if you do have any questions on that, tomorrow when we meet in lab, I will be more than happy to go over, whatever we need to with, practice problems again. We'll take a look at, anytime you guys want to do this stuff, you just holler at me. I have no problem going over, any particular problems you're being stumped by or something like that. And remember, my motto, there are no stupid questions. There are only stupid answers. So, but you should find that, Eli, and I'll post that. I'll post a link to my YouTube channel, and that way you can go, you can kind of cut out the middleman if you ever need to, and look at all my boring crap. I even have a bunch of, basically my whole residential class is all on there in video too. If anybody ever wants to go check it out. I don't know why you would, but so yeah, so I'll do that. You do that. And then we'll meet tomorrow. Sound like a plan, gentlemen?
Yeah, sounds good.
All right.
Yep.
Awesome. Then I will see you guys tomorrow morning, bright and early.
See ya.
All right, buddy.